Okay, we'll go ahead and get started now. Can you see my screen and hear me?
Yes.
Okay, thank you. All right, so today what I'd like to do is I'd like to just go through chapter 5 and chapter 6 quickly and just kind of talk about some of the concepts that we had in the two chapters. Monday, you'll have an exam on chapters 5 and 6. So just as in the past, you'll go into Canvas and take the exam through that. So we'll go through today just kind of the concepts in chapter 5 and chapter 6. I'm not going to cover really hold on. I'm not going to go through the homework problems. You can look at those, and if you have any questions, you can certainly send them to me or ask. But I want to just go through some of the concepts of 5 and 6, because I think in order to apply the equations and do things like that, you need to understand the concepts. So that's what we're going to do today. Okay, in chapter 5, that's where we talked about heat. And we introduced the concepts of thermodynamics and thermochemistry. And really what that boils down to is energy changes. And when we talk energy changes, we're usually talking about heat transfer. So either heat coming into a system or going out of a system. One of the things we talked about was in molecules, one of the things we talk about in energy is electrostatic potential energy. And here we have the equation that represents that. And we see that it's dependent upon a proportionality constant, the electrical charge of the molecules that we're talking about, and then the distance between them. And so a couple things I want to point out. In order to use this equation, we need to make sure that we have the right units. And the proportionality constant, K, is key to that. So we see it as joules, meters per coulomb squared. And since we know that energy is usually expressed in terms of joules, that tells us that our distance has to be in meters. We also know that the charge expressed in coulomb, that'll cancel out the coulomb squared. The other thing to remember when using something like this is that a joule also can be expressed as kilogram per meter squared per second squared. So another kind of piece of information when we would use this formula of what the units of the different components would have to be in. The other thing, and this was on the quiz, is that with electrostatic attraction, oppositely charged ions attract. So it's the whole old saying of opposites attract. The other thing to remember about this is when you form chemical bonds, energy is released. When you break chemical bonds, energy is consumed. So in other words, to break a chemical bond, you have to put some energy into it. When bonds are formed, energy is given off. And so that's a common theme in this chapter, is understanding if energy or heat is going into or out of the system. We talked a bit about the first law of thermodynamics, and that simply is that energy can be converted from one form or another, but energy is neither created nor destroyed. So in other words, the form of the energy changes, but we need to remember that we're not making more energy and we're not destroying energy. We're just kind of shifting the form it's in. And so that's the key to these calculations that we do. And all this discussion, this thermodynamic discussion, is that the heat isn't going away or being created, it's just shifting. A couple of terms that we defined were system and surroundings. And so when we talk about this type of energy flow, the system is that part of the universe that we're actually studying. And so it's where the reaction is taking place, where the action is taking place. The surroundings are everything else. And so in this particular example, with a couple of gases and a piston and things like that, we see that the hydrogen and oxygen gas molecules are the system. And then the surroundings are the piston, the container, all of that other stuff that is around it. And so we'll talk about things either going into or out of the system, things going into or out of the surroundings. And that's a real key thing for how we define. We talked about several types of systems, an open system, and that's where you can exchange heat and mass. So the thing we're studying exchanges heat and mass with the surroundings. A closed system, and that's where the thing we're studying only exchanges heat and the mass stays constant. And then finally, an isolated system, and it's a region that cannot exchange heat or mass with its surroundings. So the one that we're most concerned about, and the one that we talk about the most, is the closed system. And so there we're talking about keeping the mass constant, but having an exchange of heat of what we're studying with the surroundings. We introduced the concept of internal energy of a system. And we said that the internal energy is the sum of all the kinetic and the potential energies of all the components of the system. And we use the letter capital E to represent that. Since it's difficult to know what E itself is, we're usually looking at changes in internal energy. So we have an initial state and we have a final state, and we see what that difference is. So if the system loses energy, loses internal energy, the energy decreases, and so delta E would be negative. So in other words, something that's giving off energy is negative. If it's gaining energy from the surroundings, then energy is going into the system, and then delta E is positive. So that common theme of energy going in is positive, energy going out is negative. So that general idea is important that we remember that. Because as we know, in the thermodynamic type calculations, the sign of the value gives us a clue as to if it's exothermic, endothermic, things like that. So By definition, the change in internal energy, delta G, is the final energy of the system minus the initial energy. And as I said, if delta E is positive, so in other words, if the final number is bigger than the initial number, then energy was absorbed from the surroundings. So in other words, energy was put into the system. And if it's less than 0, then that final energy value is going to be less than the initial. And so that means energy was released or given off. When we talk about these thermodynamic quantities, there's 3 parts to it. There's a number and there's a unit. So number and unit is something that by now, hopefully, we've gotten used to expressing every time when we do a calculation. But the other thing, which is there all the time also, but in the thermodynamic type calculations is even more important, is the sign. And so once again, just to repeat it again, a positive delta E, you get that when the system gains energy from the surroundings. So in other words, when energy goes into the system, delta E is going to be positive. The opposite is true. When energy goes out of the system, so the system loses energy to the surroundings, then you get a negative delta E. So that sign tells us which way the energy is flowing. And as we know from this chapter, when we're talking about energy, we're usually talking about heat. When energy is exchanged, it can be exchanged as either heat, which we represent as Q, or work, which we're representing as W. So in other words, delta E equals heat plus work. Whether we're talking about heat, work, or energy, in general, what we're saying, if the system picks something up, it's a positive. It's a positive sign to that value. If it gives something off, there's a negative or negative value for that. So that doesn't matter if it's heat or work or energy. If it's gaining one of those things, the number's positive. If it's losing one of those things or giving off one of those things, then it's going to be negative. So I think it's important when you're setting up the different thermodynamic type problems that you think about how things are flowing. If it's flowing into the system, it's a plus. If it's flowing out of the system, it's a minus. And that's true whether it's heat, work, energy, whatever you're trying to solve for. And so the information you're given, you got to make sure that you have the sign correct when you're using those values. We talked about how when heat is absorbed by a system, we call that process, we say that that process is endothermic. And so the value is positive. And we said that when the heat's released, that's considered to be an exothermic process. So, and that's negative. So endothermic, heat's going in, it's a positive number. Exothermic, heat's going out, it's a negative number. Early in the semester, we talked about something called a state function. And we said state functions were things that you weren't too concerned about how you got from point A to point B. You were just interested in that state that you're in when you get to point B. And I always think of it as kind of like driving home. There's multiple ways you can get there, but really all you're concerned about is getting home. And so with state functions, what that means, if something's a state function, then we can use information and it'll add up to get us where we want to go. And we don't worry about that path. So the state is independent of the path that it took to get there. And that comes in handy in calculating some of these delta H's for the reactions. as we'll see in a little bit here. So internal energy, delta E, is a state function. So that means it depends only on the present state of the system, not on how the system arrived at whatever state it's in. And so what that means is delta E only depends on the initial and the final energy values. We said before, if you recall, we'll go back and look at this again. We said before that delta E equals heat plus work. And we said that delta E is a state function. So we're just concerned about that state when we get to the end. Heat and work are not state functions. There, the path does matter. And so while delta E is a state function, heat and work are not. So usually when we talk about work in the context of the thermodynamic stuff, is that we're talking about the mechanical work associated with the change in volume of gas. So we talked about some of these problems where the piston moves up or down and there being work associated with that. So when we say work, it's usually for those types of applications that we're concerned about. We know that for these piston type problems, we know that work is equal to minus the pressure times the change in volume. And the work is negative because it's work done by the system. So it's not work done on the system, it's done by the system. And so we know that if it's done by the system, that gives it its negative value. So there were some homework problems associated with that. I'm going to skip over those for now. You can look at those when you want. But let's move along to enthalpy. So we introduced the term enthalpy. And one of the key things is that we said if a process takes place at constant pressure, and usually we're at atmospheric pressure, so essentially that's constant pressure. And the only work done is this pressure volume work. We can account for the heat flow by measuring something called enthalpy, which we designate as H. Enthalpy is the internal energy, E, plus the product of pressure and volume. So enthalpy equals E plus PV. If we have that constant pressure, then the change in enthalpy, which we call delta H, is equal to the change of energy plus pressure times the change in volume. Okay, the pressure doesn't change because we said it's constant pressure. So that's why the pressure doesn't have a delta in front of it. So we can write this, of course, as delta H equals delta E plus P delta V. But we can further simplify it. We can further simplify it. Since delta E, we said, is equal to Q plus W. In other words, delta E is equal to heat plus work. And we also said that work is equal to minus P times that change in volume. We can substitute these things into the enthalpy equation. So if we substitute that Q plus W for delta E, and then we substitute minus P delta V for work, we see that delta H equals Q plus W minus W. The W's cancel, and we see that delta H equals Q. So if the pressure is constant, and if we're at atmospheric pressure, that's essentially constant pressure, then the change in enthalpy is based simply just the heat gained or lost. So, we talked about energy equal delta E equals Q plus W. We said that really the work only shows up on certain of those gas problems where we have the piston and things like that. This further simplifies it in that we say that delta H is only the change in heat. So heat gained or lost. This is why it's so important to understand, is it negative or positive? Because that's really what we're getting at to in a lot of these calculations. So just to repeat that positive negative thing again, if it's endothermic, remember we said that's when in this case heat energy goes in, delta H is positive. If it's exothermic, so in other words, heat is lost, energy is lost, then delta H is negative. So the change in enthalpy, delta H, is the enthalpy of the products minus the reactants. We also talked about for reactions, and there were a few versions of delta H that we talked about, but the one for a reaction is called the enthalpy of reaction, or more commonly, the heat of reaction. So this is the one that's the delta H with the little RXN subscript. The RXN is for reaction. And so that heat of reaction is just as with the other things. If it's a negative value, it means it's exothermic, and so it's giving off heat, when the reaction occurs. If it's greater than 0 and positive, then that heat of reaction would be endothermic and would mean you had to put energy into it to get the reaction to occur. So enthalpy is an extensive property. Hopefully we remember that an extensive property means that it's dependent upon the amount of stuff you have. And so think of it as something that catches on fire or explodes or something like that. If you have just a tiny bit of it, you're not too concerned about it. It's easy to contain. If you have a lot of that material and that reaction occurs, then you've got a big problem on your hands. So enthalpy is an extensive property. It's dependent upon the amount of material you have. And that's why we do some calculations where we say you have X number of grams of a material or moles of a material and want to calculate the delta H of it to give us a feel for how much energy is involved with that amount of material that we're using. When we have a reaction and we have a value for delta H of that reaction, that delta H is for the reaction going in that direction as written. If we have the reaction go the opposite way, the magnitude of the delta H value stays the same. So in other words, the number stays the same, but the sign would change. So if it's an exothermic reaction and say it's minus 100 joules, for instance, if we went the opposite way for the reaction, it would be a positive 100 joules. The other thing about these enthalpy changes is, if you recall, when we write molecular formulas, or rather equations, we often have a little G or S or L in parentheses next to the molecular formula of each of the compounds. Enthalpy changes do depend on the state of the reactants in the products. So you're going to have different values for solids versus liquids versus gases, even if the compound is the same. So it is important when you're using those kind of tables, for instance, that you get the right form of the compound. We talked a bit about calorimetry, and calorimetry is simply an experimental way to measure heat flow. You'll do a simple calorimetric experiment next semester using one of these types of styrofoam cup type calorimeters. And so it's a way by checking the temperature of, in this case, of water before and after you do the reaction, you get a feel for what that heat flow is. Related to that is materials have heat capacity. And so let's talk about heat capacity and specific heat. So heat capacity is defined as the amount of energy required to raise the temperature of something by 1 K or 1 degree Celsius. If you're talking about the amount of substance that's being heated is 1 gram, then it's called specific heat, and that's C sub S. If you are talking about an amount that is 1 mole, then that's the molar heat capacity, which is C sub M. So the expectation is that you know the differences between heat capacity, specific heat, and molar heat capacity, and that you can work with any of those and be able to express any of those given certain information. So for instance, if you were given that you had a certain number of grams of something and a heat capacity, you should be able to calculate the specific heat. Same with the molar heat capacity. The specific heat equation is the amount of heat that's transferred, Q, divided by the mass, grams of substance, times the change in temperature. So you should be familiar with this equation and know how to use it. One of the key things is remembering that you need to have the mass in grams. Temperature can be Kelvin or C, it doesn't matter because you're doing a difference, but the mass has to be in grams. The formula, the equation down at the bottom is just a rearrangement of the previous equation there. So in that case, you're solving for heat rather than solving for specific heat, but it's just in a rearrangement of those terms. Here's some more information about calorimetry. A little discussion about bomb calorimeter. What's different there is you have that heat of reaction is equal to the change in temperature times minus the constant of the calorimeter. So the constant of the calorimeter would be something that you would determine experimentally and just takes into account the impact that the instrument is having. Okay, let's talk about Hess's law for a little bit. So there are delta H values that have been determined for a lot of different reactions. And so because you would like to not have to be determining these delta H values every time you do something different, we can take advantage of the fact that this delta H is a state function, and we can calculate delta H using delta H values for these intermediate reactions, as long as all those reactions add up to give us the final reaction. So what we can do is we can take the delta H value for different steps that are in that reaction, and we can add them up as long as we are using the right signs on the individual steps, and we'll get the same answer as we would if we had just the direct measurement of the reaction. So that's pretty useful. And we had some examples of these things in the homework. I would go back and take a look at these to make sure you're comfortable with them. Let's talk about the enthalpies of formation for a bit. So enthalpy of formation, another one of these delta H values, and this one we have the F subscript. And that's the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental form. So it's all more commonly known as the heat of formation. And this gives us information on the formation of certain compounds from their more base state. Heats of formation are measured under standard temperature conditions, standard temperature and pressure, STP. The temperature is 25 C and the pressure is 1 atmosphere. And this is just a table of some of these compounds so you can get a feel for the range, pretty wide range of values. We also can use that information for individual things, but we also can use these reactions to piece together what the delta H for a different reaction would be. And so in this case, we have the example of propane plus oxygen going to form CO2 and water. So first of all, we remember that this is a combustion reaction because we have oxygen as one of the reactants, and we're forming CO2 and water. So that's our definition of a combustion reaction. And so rather than having to figure out what this delta H is, we can use some known delta H values and piece those together to get what it is for this overall reaction. So here we have decomposition of propane. So propane going to graphite and hydrogen. So we know a delta H value for that. Then we have the formation of CO2. So we have graphite plus oxygen going to CO2. Then we have the formation of water, where we have hydrogen plus oxygen to give us water. So we have those three reactions. So we look at those three reactions there. And what we're going to do now is we're going to look at those and see if that pieces together to give us our final reaction. And if we look at that, we see if we sum up these three reactions, we see that the H2s cancel because they're the same on the reactant side and the product side. We see that we can add the O2s. We have 5 O2s. We see the propane is fine. And then we look at the CO2s. We have 3 CO2s, and then we have 4 waters. So all of those individual reactions add up to give us this final reaction that we're interested in. So what that means is we can use those delta H values for the individual reactions to find out what the delta H is for our final equation. So Hess's law tells us that delta H of products is delta H is equal to the delta H of the products minus the reactants, where N and M are stoichiometric coefficients. So the stoichiometric coefficients in this case would be 1 on the propane, 5 on the oxygen, 3 on the CO2, and 4 on the water. So we need to take those into account also. And here we are doing that. We said it's products minus reactants. So we used heat of formation of CO2, 3 times that value, 4 times the value for water, and then minus 1 times the propane value, plus 50 times, in this case, rather 5 times, in this case, 0, because O2 value is 0. All of that is negative because we have to change the sign on that because we're not forming those, we're decomposing those. And then we get our final answer. So we're able to take information we know about the individual steps and get to a delta H for the overall reaction. We also talked about bond enthalpy. And in this case, we were looking at gaseous molecules. We remember that to break a bond, we have to put energy into it. So that would be positive. If we form a bond, energy is released. So that would be negative. We also know that the greater the bond enthalpy, the stronger the bond. And these are just some bond enthalpy values. So in other words, the higher the value, the stronger the bond. If we add all the bond energies for the bonds that are broken and subtract the bond energy for all the bonds made, then the result is our delta H for the reaction. So bond enthalpies of bonds broken minus the sum of bond enthalpies of bonds formed. So that kind of takes us through chapter 5. Any questions about 5? Okay, let me pull up 6 here. Okay, hopefully you're seeing chapter 6 now. So in chapter 6, we started talking about electronic structure. And what that means is we're talking about the arrangement of the electrons and the energy levels of the electrons. And we also started talking about the duality theory of waves and photons and things like that. In this week's lab, you'll get a nice example of what some of this stuff looks like visually. So hopefully that'll help with you understanding it as well. But let's go ahead and let's review this material. So when we talk about waves, that's important in understanding electromagnetic radiation. So when we talk about electromagnetic radiation, what we're talking about is light. And light moves as waves. And it moves at the speed of light. So speed of light, you've heard of that term before. A wave in the cartoon here, they're showing it as like a wave in an ocean, and that's really what we're talking about. And so the distance between those crests and the wave is called the wavelength. So literally the wavelength. So that upside down Y is the symbol for that, lambda. And so we express the size of the wave as its wavelength. The length of its wave is its wavelength. We also talked about something called frequency. So frequency is the number of waves that go through a given point per unit time. And so if you see frequency, it can be expressed in terms of 1 over seconds. It can be expressed as seconds to the -1. It can be expressed as hertz, H with a small z. So don't get confused by the units. All 3 of those are commonly used. So you should be aware that s to the -1, 1 over s, and hz all are saying the same thing. They're all units for frequency. When we talk about light, we say it has both wave and particle properties, so it's that duality, and that the particles are expressed as photons, and we'll talk about that a little bit later. But the key is that those photons have distinct energy values. And how do we relate that energy? Well, as I said before, wavelength, the upside down Y, lambda, this is inversely proportional to the energy. So energy is proportional to 1 over the wavelength. So what that means is the bigger the wavelength, the longer the wavelength, the less the energy. And so that energy of the photon is inversely proportional to wavelength. Now, the frequency, which is kind of represented by the little V looking character, which is nu in the Greek letter nu. The frequency is inversely proportional to wavelength, just like the energy was. So frequency equals the speed of light divided by wavelength. So this relationship you should know, you should be familiar with it, be able to use it. The thing I want to point out that's important on this is let's look at the units for C, the speed of light. The units on that is meters per second. So what that tells me is if I want my units of frequency, if those have to be 1/2 or second to the -1 or hertz, then I have to be able to cancel out the meters unit in this formula. The only way I can do that is if my wavelength is expressed in meters. Well, wavelengths usually are not expressed in meters, especially in chemistry type applications. So they might be in nanometers or micrometers or something like that. So what that means is in order to use this equation, use this relationship, you have to convert the wavelength into meters. So make sure you're comfortable with doing that if you're going to use this conversion to go between frequency and wavelength. Because sometimes you might be given a frequency and you need to convert to wavelength. Sometimes you might be given a wavelength, you need to convert to frequency to use some of these other equations. Here just reinforces what that light spectrum looks like, starting with gamma rays to X-rays, UV, then vis, infrared, microwaves, radio waves, showing that as the wavelengths get bigger, the energy decreases. And we see that at the lower wavelengths, you have that inverse proportionality with frequency. So the frequency is higher. Down at the bottom of this slide, we have a couple things I want to point out. One is that value for the speed of light, 3.00 times 10 to the 8th meters per second. And we see that we can rearrange that equation that we looked at a little while ago to show that the speed of light is equal to the wavelength times the frequency. And once again, that means the frequency, the wavelength has to be in meters. So table 6.1 is similar to something that we covered earlier in the semester with these symbols and these prefixes. So if you don't remember them or didn't learn them earlier this semester, now's a good time to learn them. This is definitely something you will need to know. So things like angstrom, that's that capital A with the little circle on top. That's equal to 10 to the minus 10th meters. Nanometers, the small n in front of m, that's 10 to the minus 9th meters. Micrometer, that micro symbol looks kind of like a U in front of the m, that's 10 to the minus 6 meters. Millimeter, 10 to the minus 3 meters. Centimeters, 10 to the minus 2 meters. Those are all prefixes and conversions you should be familiar with. Well, when we talk about the electronic properties of light, there are some things that aren't explained by the wave theory. And this is what led to the energy packet, the photon, the quanta, that type of thinking. And so if you recall, the three things that we said that pertain to light, that pertain to the radiation, that couldn't be explained by waves were the emission of light from hot objects. So in other words, you think of some object that you heated up enough and you'll sometimes get light emitted. That's called black body radiation. The emission of electrons from metal surfaces on which you shine a light on, that's called the photoelectric effect. And then the emission of light from electronically excited gas atoms. So if you get gas atoms excited and you get the right frequency of light on them, you'll get emission of light from that, and that's an emission spectra. This emission technique is how most analyses, if you ever see low levels of metals, like low level of iron numbers or things like that, it's done through techniques that leverage emission spectra. So we talked about how that wave idea doesn't explain, in this case, the material being heated up and it emitting light. And that's where Planck proposed that energy could be released or absorbed by atoms only in discrete, what he called chunks. And the chunks of energy come in packets called quanta, and so energy equals Planck's constant times the frequency. He also said that the energy can only be emitted or absorbed in intervals of the constant times the frequency. So it's not just any random energy that it can be. It has to be defined energy levels. And so these allowed or defined energies, we call that as being quantized. So Einstein built upon this to explain the photoelectric effect. Remember, that's where if you have a real clean metal surface, you can shine light on it. And if the light is at the right frequency, then you will get emission of electrons. And so if you don't have the right frequency of energy coming in, then you don't get that emission. It doesn't matter how intense it is. If it isn't at the right frequency, it won't do this. And from this is where the phrase, the term photon came. So these energy packets became known as photons. In other words, they have the proper frequency to cause the emission. We talked about certain amount of energy that's needed. If the photons have less energy we get from this formula, then we know that nothing's going to happen. So you can increase the intensity of the light source, but if it's at the wrong frequency, you're not going to get the emission. It has to be the right frequency. Atomic emissions was another one that led to this. And so we talked a little bit about a continuous spectrum and a line spectrum. So continuous example of a continuous spectrum would be the lights in a room. So you have a series of wavelengths that are being emitted from that source. Whereas with a line spectrum, there's only certain wavelengths that you see. And so each element has a unique set of emission spectra. So here we have an example of hydrogen and neon, and we see those. But by looking at the emission spectrum from an element, you can determine what element it is. These emission wavelengths are known, and by looking at what they are, you can tell whether it's neon, hydrogen, or whatever. So Rydberg had studied the hydrogen spectrum and had come up with a formula, which we see here. The RH is a constant named after him. And then Bohr expanded on this and started explaining some of this stuff. So what he talked about is that an electron is permitted only in certain allowed energy states. And he also said that energy is emitted or absorbed by the electron only as the electron changes from one of these energy states to another. And that energy, which we're calling the photon, is defined by that energy equals h times the frequency. So we started getting with Bohr this definition of defined levels that the electron can be at. And so we call that lowest energy state for the electron, we call it the ground state as a value of n equals 1. And we'll talk about n being the principal quantum number in a moment. Higher energy levels are called excited states. And so then those are just 2, 3, 4 on down the line. We can calculate that energy change from one level to another using the formula below here. If the energy change is positive, so final is greater than initial, that means energy was absorbed. So in this discussion, that means a photon is absorbed. If it's negative, if the final is less than the initial, then that means that photon has been released, energy has been released, and you get emission of the photon. That energy of the photon always equals the energy between the two states. If it's not the right amount of energy, then this doesn't work. Well, the Bohr thing sounds pretty good, except it only works for hydrogen. So there's a lot more, obviously, to chemistry than hydrogen, so that was a big limitation of Bohr. But there were a couple things that held up from the Bohr model that we want to remember. And that is electrons exist only in discrete energy levels, which are described by the quantum numbers. We'll go through the quantum numbers again in a moment here. And that energy is involved in the transition of an electron from one level to another. So electrons exist in discrete energy levels described by the quantum numbers, and energy is involved in the transition of an electron from one level to another. So de Broglie said that matter should have wave properties also, and he had developed a relationship between mass and wavelength. So he said that wavelength is equal to Planck's constant divided by mass times velocity. And remember, we had previously defined mass times velocity is equal to momentum. So what he's saying is that wavelength is equal to Planck's constant divided by momentum. So that led us to the start of quantum mechanics. And so Heisenberg developed something called the uncertainty principle. The Heisenberg uncertainty principle says that the more precisely you know the momentum of a particle, the less you know about its position. Schrodinger further developed this and added the math to it. So you'll hear about, if you continue on to P-Chem, you hear about Schrodinger's equation. And so the big thing about this is the Schrodinger equation in the Schrodinger math led to something that a discipline known as quantum mechanics. And for us right now, the big thing that we get from quantum mechanics that we're interested in is it starts to help us visualize where these electrons are located. And it helps us understand visually orbitals and things like that. And so in this dot density plot that we have here, we see a bunch of blue. The blue dots, the more blue dots there are, the more probability that that's where the electron is. And so as you can see, there's a lot of places where the electron can be, but really in this case, it's all around the center here, so around the nucleus of the atom. And so this is what you're going to do in lab this week. You're going to play with some software that helps you visualize these atomic orbitals. And so you'll get a better feel for what they look like in a three-dimensional situation. As I said, Schrodinger did these calculations, wave functions. The wave function is typically squared. That's the psi squared, so the little pitchfork looking thing with the 2 psi squared. And that gives us those electron density maps, which we have on the right here, and which tells us the probability of where that electron can be at any one time. Okay, so you solve these wave equations, gives you the wave functions, which we call orbitals, and their corresponding energies. The orbitals describe that spatial distribution of the electrons, and we describe the orbital by a set of 3 quantum numbers. And so let's discuss those quantum numbers for a bit. So the first one we talk about is the principal quantum number, designated as N. And the principal quantum number tells us the energy level on which the orbital resides. The values for N are integers, starting at 1 and going up from there. As that N value increases, the orbital becomes larger, and the electron spends more time further away from the nucleus. The bigger the N number, the higher the energy that the electron has, and the less tightly it is bound to the nucleus. So in 1 and 2 and 3 and 4, as we go up, orbital gets bigger, electrons get a little more spread out from the nucleus, and the electron has higher energy and less tightly bound to the nucleus. The second quantum number we talk about is the angular momentum quantum number, L. And with this number, while the first quantum number told us the energy, the second quantum number tells us the shape of the orbital. And like I said, this is what you're really going to get a nice feel for after lab this week of playing with the software, is you'll see what these orbitals look like. Now, the allowed values for this are integers once again, and it goes from 0 to N minus 1. So we use that N value on the energy level, that principal quantum number, and we subtract 1 from us, and that tells us for at that energy level how many shapes there are. So we say that we can calculate these numbers, and in this table here we see values of L 0, 1, 2, 3. But when we talk about it and write it in electron configurations and stuff like that, we don't use the numbers, we use the letters. So the expectation is that you will know that a value of 0 means S, 1 means P, 2 means D, and 3 means F. So we usually don't say the value of L, we use these letter designations. So you should know this. Then finally, the third one is the magnetic quantum number.
Are you doing a Zoom call?
Yeah.
Okay, don't mind.
The magnetic quantum number describes the three-dimensional orientation of the orbital. Allowed values of M sub L range from minus L to L and include 0. And so what that means is when you look at the energy levels, for energy level 1, so you have 1 s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals, and on down the line. The shell with the principal quantum number N consists of exactly N subshells, and each subshell consists of a specific number of orbitals. The total number of orbitals in a shell is N squared, where N is the principal quantum number of the shell. So this next slide, this table 6.2, this is really going to be a good one for you to become familiar with and be comfortable with. Because what it walks us through here is that we see, for instance, the N value, and we see then the subshells for that N value. So let's just go through a couple of these. So for N equals 1, that tells us that L is 0. And so then that designation is 1s. The possible values of M sub L are 0. And so then we know that there's 1 orbital in the subshell. If we go to N equals 2, then we can have possible values of L of 0 and 1. That gives us the subshell designation of 2s and 2p. In the 2s level, once again, possible M sub L value is just 0. So one of those, 1 orbital in that subshell. P can be 1, 0, and minus 1. So that means we have 3 orbitals in that subshell. So we have the 1 orbital from the 2s, the 3 orbitals from the 2p. So we have a total of 4 orbitals in that 2 shell. And then on similar thinking with N equals 3 and N equals 4. So I'd ask you to spend some time looking at this, get comfortable with this, so understanding that relationship between the principal quantum number and then the other 2 quantum numbers, and what that means in terms of knowing how many electrons are going to be present. Let's take a little bit of time looking at the shapes of these. So s orbitals, and once again, you'll get a better picture of this in the lab this week. S orbitals are spherical in shape. As you see, as you go from 1s, 2s, 3s, they get bigger. That size increases. The other thing we know from that, if we look at these radial probability plots down at the bottom, we see as we go from 1s to 2s to 3s, we start to get nodes, and we also see that the most probable distance for the electron starts to move away from the nucleus as we go up to the bigger energy levels. P orbitals have lobes. And so remember, we said that second quantum number, in this case represented by P, that tells us the shape, and we see each of these has the same shape, which is the orientation varies, which is that 3rd quantum number. And what this is telling us is that in the middle, we don't see probability of the electron, and that's that node in between the 2 nodes. D orbital, it gets a little more complex. We see here the 5 different d orbitals. 4 of them look pretty similar, just the orientation is different, where we have the 4 lobes. And then the 5th one, we have 2 lobes, then we have like the donut thing around the middle. And then finally, F here says that that's a little more complicated. you'll get a much better look at what F looks like, and you'll see what this means in the lab this week. When you look at energy levels and talk about hydrogen, we say something about, and drawing it this way, that each of these boxes represents an orbital. And you see the n equals 1, then we go to n equals 2, where we have 2s and 2p subshells. Those are at the same energy level. 3 is drawn at the same energy level as well. When orbitals are at the same energy level, we call that degenerate. The problem with this is that it's not correct. What you really have is, as you have all these electrons, you don't have the whole energy level as degenerate. You have the orbitals within the energy level are degenerate. So in other words, the same energy, but not the whole level. So we see that here. We go 1s, then we go 2s, and we see 2s and 2p. 2p is at a slightly higher energy level than 2s. Then we have 3s, we have 3p. Even those are both n equals 3, we see they're at different energy levels. Then it even gets a little more complicated, because now instead of 3d being the next energy level, 4s is actually lower energy than 3d. So then we have 4s, 3d, 4p. What you do see, however, on the p and d orbitals, you see that the 3p orbitals are at the same energy level, the 5d orbitals are at the same energy level. So in terms of within those orbital levels, those subshells, you get that is degenerate. And then finally, the last quantum number that we mentioned was the spin quantum number, m sub s. And there's only 2 values for this, plus a half or minus a half. And this shows us that this shows us the spin, and when we do our electron configurations, this is what we're representing with the arrow pointing up or the arrow pointing down. And we'll have some examples of that in a moment. Pauli exclusion principle, remember that no 2 electrons in the same atom can have the same set of 4 quantum numbers. That means that no 2 electrons in the same atom can have the exact same energy. And this leads us to electron configuration. This tells us how the electrons are distributed throughout those different orbitals. And the lowest energy one is the most stable, and that is called the ground state. We express this, and here's the example with 4p5 at the bottom. The number is the energy level, that's that principal quantum number. The letter is the type of orbital, that's the second quantum number. And then the superscript, in this case, the 5, that's the number of electrons in this 4p orbital in this case. When we do orbital diagrams, we often do it with a box, and the box represents an orbital. The half arrows represent electrons, and the direction of the electron is the spin. And so by convention, you always first draw the arrow that points up and then fill in with arrows that point down. Hund's rule tells us that when we're filling degenerate orbitals, the lowest energy is when all the electrons have the same spin. And so a good example of that is nitrogen, number 7 there, of where the 1s and 2s orbitals are full, the 2p is not full, it's half filled. And instead of pairing up those electrons, we have them all drawn with the arrow facing up. We often write kind of a shorthand version of electron configuration, which highlights the valence electrons. The valence electrons are the electrons in the outermost shell, and those are the ones that are usually involved in reactions and things like that. So those are the ones that we're most concerned about usually. The core electrons, or the inner shell electrons, are the completed shell through the noble gas that is the closest noble gas to the one that we're looking at, the element that we're looking at. So the way we do that is, let me just go back here a second. The way we do that, you see some examples here. For instance, with the lithium, you see the helium in the square brackets. that implies all the electrons are in helium, and then the 2s1, those are the valence electrons for lithium, and then kind of on down the line. The other thing you notice in these columns is they have, while they're different energy levels, they have the same number of valence electrons. In this case, they all have 1. Transition metals, a little bit different there, because then you start filling up the D shell. Lanthanides, actinides, you start filling up the F sublevel. And this table here, I think, is a real important one. You see here, over on the left-hand side in the blue, you have the S orbitals filled. In the middle with the transition elements, in the kind of orangish, you have the D filled. You see down below that in the kind of tan color, you have the F ones filled. And then finally on the right, you have, in the pink, you have the P orbitals filled. So understanding that this is how the electrons fill most of the time, you see most is bolded there. There are some exceptions, but most of the time you fill in this order. You fill the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, on down the line. So spend some time looking at this, making sure you're comfortable with how these fill. So a couple examples that are a little different, and you should know these. Let's look at chromium and copper. So we see that for chromium, it fills as argon, then 4s1, 3d5, rather than what you would probably think if you just filled them normally as 4s2 and 3d4. That's because you get more stability, thus lower energy, by having half-filled shells for the S and the D shells. Copper is similar, where copper is the argon base, inner core, then 4s1, 3d10, where you would think it would be 4s2, 3d9, but by having a half-filled 4s orbital and a fully filled 3d10 orbital, that's more stable and thus lower energy, so that one occurs. And that's it for the summary of chapters 5 and 6. So if no one has any questions, that'll be it for today. Remember, Monday is the exam. It'll be posted on Canvas. And so if you have any question or anything, just let me know. Otherwise, thank you.